Hi everyone, welcome to Introduction to Astronomy for December. Just a bit about the program for the rest of the year. Next week, Jenny McCormick is going to talk about the work she's been doing at her home observatory. And then the week after that, we will be doing a review of the summer night sky. Obviously, those two meetings will be online, but we have January off as normal. But we're hoping to resume at the start home from the first Monday of February, all going well. So just be aware of that. We will bring everyone up to date when the February journal comes out and try to get it out a bit early. Anyway, on to tonight's talk. I'm just filling in for Chris Benton. Next year, Chris will be intends to be back with the Introduction to Astronomy series. And I thought I would just do a delve into the history of how we got here, going to even prehistoric times and to the current kind of view of the universe. So start off by stating what is a fairly modern idea called the Copernican Principle. It says that humans on the Earth or the solar system are not privileged observers of the universe. In other words, doesn't matter where you are, the universe really works the same way. The laws of the universe are the same. There's no particular place which is privileged. We're on the Earth and it's our home for sure, but in physical terms, we could just as easily be on a planet orbiting a star in Andromeda or anywhere else, and the universe would essentially follow the same laws. But things weren't always like that, as I'm sure you're aware. So we'll start off with the ancient world, even going back into the Paleolithic, and find out how ideas developed over that time. We'll look into it. It's going to be a fairly cursory glance. There's not a lot known about some of these things until we get to classical times, where we have a lot of written or copies of written records available. So the Paleolithic, what do we mean by that? It literally means the old Stone Age, and it refers to the type of durable tools that were used, basically shaped stone. And because stone is very durable, we find a lot of archaeological evidence of this, things like arrowheads, spearheads, scraping tools, things like that. I'm sure they used other materials as well, but those sort of things are perishable, and wood and things like that would decay over many thousands of years. So archaeologists tell us that people in those days lived a hunter-gatherer lifestyle. They had to basically go where the food was, follow the seasonal migrations, and they would only have temporary settlements where they would stay while the food source was good, and then move on. So this period actually covers the majority of the time that humans have existed. Basically humans have been around for about 100,000 years, and most of that time this was the way people lived. And there is some other evidence apart from stone tools. There are also rock paintings, which are sometimes found in caves, especially where such paintings are protected from the elements, and of course fossil remains. So some studies have claimed that certain rock art shows evidence of some kind of calendar system, so some way of predicting the system, the seasons, and it's probably likely that people, especially living in temperate latitudes, would be keen to be able to predict when the seasons were changing, because that was tied to the kind of food sources that were available. But there's not really any direct evidence. This is a famous rock art that's quite extensive actually, but this is showing one portion of rock art in a cave in Lascaux in France. It dates somewhere between 15 and 17,000 years ago. And there's some controversy about this. You notice the image of what would be an auroch, which is the ancestor of modern day cattle, but a wild cattle called an auroch. And you notice there are some dots marked around the place. And some archaeologists have asserted that these are actually represent stars, and that in fact what we're looking at is the constellation of Taurus with the Pleiades, with that group of dots to the right, upper right, and the V triangle of the head of Taurus in the modern constellation. Now, it seems pretty unlikely, but it's possible because that this part of the sky was associated with a bull-like creature, because this kind of thing would be passed down, or could easily be imagined it would be passed down for generations. People say, oh yeah, that's a bull. And so it is plausible, but it's not generally accepted by archaeologists. But it's very interesting if true. It shows that people in those times were really interested in the night sky, probably used it for marking the flow of the seasons and so on. Come to a much more recent time called the Neolithic, just means new Stone Age. And this period is basically since the end of the last glacial period, conditions greatly improved, much better sources of food as the climate warmed. And because it would have been very harsh in Ice Age conditions to scratch out a living in especially northern places in like Europe and the parts of the Eurasian continent. So this heralded totally new technologies. We had, for the first time, we see evidence of farming, in other words, growing crops rather than just foraging to find suitable plants. And there's herding of animals, pottery, and people tending to start living in fixed settlements. Hunter-gathering still went on, but there was a gradual change of lifestyle to, I guess, a more settled way of life, because you had to stay around to tend your crops or your herd of animals, although some herders did move around with the herds. So this period started about 11,500 years ago. And we're fairly sure that at this time, especially related to farming, it became important, even more important, to mark the seasons, to know when to prepare for planting and things like that, harvesting. And as a pretty universal scheme with a lot of cultures around the world is to use the heliacal rising of particular stars, or as in this country, star clusters, the example being the heliacal rising of Matariki. As the time goes on during the year, different stars appear in the dawn sky before sunrise. And so this was a way of basically knowing what time of year it was. Some examples, apart from Matariki, is in ancient Egypt, Sirius was used in the same way because it was a foretelling of the annual flooding of the River Nile. The other thing that we find is around different places around the world setting up artificial markers to mark things like the rising and setting positions of the sun and moon. And probably the most famous one of these, or most well known, is Stonehenge. So this was built actually in the late Neolithic, and it was finished by a totally different set of people. The people that finished it were really early Bronze Age people that migrated into the UK by bringing in farming methods, whereas the people that started Stonehenge were actually hadn't really discovered farming. So it's quite interesting. It shows that early Neolithic people were able to build monuments like this, which is quite interesting. And this diagram shows some example. You can see at the top there the the solstice sun shining through the gap and lined up with the heel stone. And the diagram below shows how the alignments work. You have an alignment for the summer solstice sunrise and the sunset, and same thing for the winter solstice, where the sun, and this is the northern hemisphere, so in the winter the sun setting and rising a lot further south, and in the summer rising and setting further north of west and east, and as you can see there. So this is a really interesting example in South America, where that's called the Towers of Chanculo in Peru. And they were doing a similar thing here, but what they would do is have an observing position on either side of this row of towers that were built along the top of the ridge. There are 13 of them. And what it's doing, it's used to mark the position of the sun as the year moves on. So you have the winter solstice at one end and the summer solstice at the other, and the equinox is in the middle. So they could use this as a really easy way to monitor the position of the sun during the course of the year. So it's really quite fascinating, I think. Another example was on the island of Oahu. The Hawaiians had a number of sites where they would set up stones that were aligned to particular landmarks, and they were observing positions of the sun, moon, and things like that, astronomical, where they, instead of basically relying on setting up huge megaliths such as Stonehenge, they would just line up with a natural object like the top of a peak on a mountain and things like that, some marker on the landscape. There's a reasonable amount of evidence to show that's what they were doing. So we're going to jump ahead to the early Bronze Age, and this isn't so much to do with astronomy, but it's really important development is the invention of writing. And there's a particular reason I picked on Sumer, apart from the fact that their writing system was one of the earliest. As you can see on the left there, they started with basically pictographs, which is similar concept to the Egyptian hieroglyphs and the Chinese alphabet, or not really an alphabet, but the Chinese lettering system or writing system. So they were basically representative of some kind of thing or concept, and so they weren't needed for any particular language. But unlike the Egypt and China, Sumer rapidly modified their system to a far more abstract system, and also they changed it so that rather than the symbols representing things or concepts, they came to represent syllables. So you could say the syllable, which might have been the name of a particular thing, but you could put them together to make words. And that was possibly the first time that had been done. It's not quite the same as an alphabet, but it's sort of intermediate between pictographs and an alphabet. The interesting thing about it is that they were surrounded by neighbours who spoke languages that were totally unrelated to theirs. They had what's called an isolate language, a little bit like modern day Basque. And but the neighbours actually picked up this writing system and wrote their own languages in it. So it was used for Babylonian, Elamite, Hittite, and Old Persian. You've got Semitic languages, Indo-European languages, all using the same writing system. They couldn't understand each other, but if they saw the cuneiform, as it's called, they could actually say the words, even if they didn't know what they meant. And the reason scholars can understand this today is mainly because the old Persian kings actually had a number of treatises carved into rocks in the different languages. And it happened that the Sumerian language had been retained as a kind of liturgical language or scholarly language, if you like. So any highly educated people knew it, and even though it was no longer spoken as a common language, but it means that modern day scholars have been able to decipher it. And this is the connection with astronomy. I was just going to say the reason they did that kind of style of writing, use those funny wedged versions, that it was really easy to reproduce that in clay. So if you did it in soft clay, you could pass on a message. And if it was a temporary one, you could just smooth it off, write another message. But if it was important, you would fire it, and the message was now permanent. Well, sometimes these things were accidentally fired because they were just burned in a fire, like a house fire, something like that. So we have a lot of the basic mundane type of tablets saying, like a shopping list or a list of somebody's animals, things like that. Interesting thing, and the influence Sumerians have had right up to modern times is their numbering system. They used a base 60 system, and the idea was, or the theory is that they chose this because you had your four fingers on one hand have 12 joints, and you could use your thumb on that hand to point at a particular joint and use the 5 digits as the other hand as a multiplier. So you had a base 60 numbering system. They divided the circle into 360 degrees. And so Babylon and later the Greeks picked up this system, and it's basically still in use today for measuring angles and also units of time. So the Sumerians aren't around anymore, but their legacy still lives on. So this picture here sort of gives us an idea of what we think Neolithic and early Bronze Age people thought about the universe. That basically the world was flat, and there was some kind of dome that held the stars, planets, moon, and sun on the sky. And then you see the shepherd looking out the other side of the dome and seeing some kind of strange mechanism that's operating it all. So we don't know for sure, but it's highly probable that people in those days thought that if they did think about it at all, that's how the world worked. So now jumping into classical Greece and Rome. So the first person I want to talk about here, from now on, we actually have written evidence of particular people. We know the authorship or their work was copied, so quite a lot of it survives in that form to the current days. Aristotle was probably the most influential of the Greek philosophers, and he has a treatise here on the shape of the Earth. So he says, in lunar eclipses, the outline of the eclipse is always curved, and he's talking about the shadow of the Earth on the surface of the moon. And since it's the interposition of the Earth that makes the eclipse, the form of this line will be caused by the form of the Earth's surface, which is therefore spherical. So you'll be aware that a lunar eclipse, depending on where you are and the time it occurs at your location, can be anywhere in the sky at night, obviously. But if you see the eclipse when the moon is low down, or maybe the end or the beginning of the eclipse, the Earth's shadow is curved, and it doesn't matter what position you see the moon in the sky, it's always a curved shadow. And the only possible shape that can cause that is a sphere. Aristotle realized that and basically convinced all the other Greek scholars that this was the case. He also noted that our observation make it evident that not only is the Earth is spherical, but it is of no great size. In other words, he says that if you go a relatively small way north or south, you notice different stars come into view. There's a manifest alteration of the horizon without having to travel all that far. So he contended that, and correctly so, that the Earth is not actually all that big. Unfortunately, Aristotle was a geocentrist, although he believed the Earth was a sphere, he thought that basically the heavens rotated around the Earth. And because he was so influential, this concept really swayed people for probably nearly 2,000 years. However, not all Greeks believed this. So I give the example of Epicurus, who I think was mentioned in passing in the monthly meeting last month. He was born on the island of Samos, the same place as Pythagoras, if you've heard of him. Samos, actually, quite a lot of interesting people were born there, a small island off the coast of modern-day Turkey. He was what was known as the Greek philosophy school of the atomists. So he believed the Earth, or the world, if you like, was composed of two primary constituents. So you had eternal, ever-moving and colliding atoms grouped in moving macroscopic object, and the other component was empty space or void. And Epicurus reasoned that empty space must exist, otherwise atoms couldn't move. So it seems kind of reasonable, but he pondered the idea of the human soul, or the concept of soul that the Greeks had. And he thought he couldn't really understand this, so he thought that souls must be made of a special type of atom. So the atomists believed that the void and atoms were of infinite extent and the universe is boundless, and therefore there must be infinitely many worlds in the universe, which is quite interesting to something well over 2,000 years ago. This is a philosophical thing, though. It's got nothing directly to do with what astronomers do, which is actually observing the night sky. So we come now to an actual astronomer who was also a theoretician, another one born on Samos, and he proposed that the Earth was actually just a planet like the other planets, and they were all orbiting the sun. So this was the first proposition of or that we know of a heliocentric model of the universe. And because unfortunately we know that he wrote a lot of stuff on astronomy, but unfortunately very little of it survives, probably because heliocentric astronomy was considered to be fringe at the time, so there was no compunction to copy his works or preserve it. So very little survives. There's only but he is referred to by other writers, and we know some interesting things that he did. One of the objections that others had against the heliocentric model was that every 6 months, if that were true, if the Earth was orbiting the sun once a year, every 6 months you should see a semi-annual parallax effect of the stars, that their position should be shifting slightly relative to stars that were further away, assuming they're not all at one fixed distance. So Aristarchus said, well, it's just the stars are so far away, we can't measure the parallax, but it was sort of an open question. But he did do some interesting work on the dimensions of the solar system, and we'll have a quick talk about that. Okay, so here's one of the ideas he came up with, measuring the relative distance to the sun. He didn't have any obvious way to measure the actual distance, but he figured out the scheme for measuring the ratio of the distance of the Earth to the moon versus the Earth to the sun. And he thought, okay, when the three bodies are in this alignment, and this is highly exaggerated, in actual fact, the sun would be way, way off to the left of the page, and also the moon would actually be further away and smaller. But it's just to illustrate, when the lunar terminator is exactly at a half a moon, you know that the line between sun, moon, Earth is exactly a right angle because you're basically seeing the terminator separating the side of the moon in shadow and the sunlit side of the moon. Seems like a really clever idea, and if you can observe, of course, that these type of moon during the day when the sun is in the sky, so you can, in theory, measure the angle between the sun and the moon as measured at the Earth. And using a bit of geometry from that, you can work out the ratio of the distance of the moon and the distance of the sun from the Earth. The problem is measuring that angle is not that easy. Telling exactly when the terminator is right at the half point, not that easy. And it turns out, because the sun is so far away, a tiny error in the measurement of that angle makes a big difference in the distance. So Aristarchus thought that the angle was about 87 degrees. It's actually 89 minutes 50 seconds. So Aristarchus came up with a number that the sun is 20 times further away than the moon. It's actually 400, roughly 400 times. But nobody did any better for more than 2,000 years. So the actual method is right in theory. The problem is the measurement is difficult, and it also is highly prone to a small error leading to a big difference in the answer. Another thing clever idea he came up with, we don't know the exact method he used, but it was to do with the moon passing through the shadow of the Earth at the time of a lunar eclipse. And he came up with a scheme basing on how long it took the moon to pass through the shadow, and a bit of geometry. He came up with an answer that the Earth is about 2.5 times as big as the moon in diameter. Did a bit better this time. The actual value is around 3.7 times. We don't know the exact detail of the method because his work is lost, and it's only referenced in another paper where they don't describe the exact method that he used. So we come a bit later on, we've now at Eratosthenes. So another important measurement in astronomy is, how do we know the size of the Earth? Working out the ratio of something is all very good, but it would be nice to know its actual size. So Eratosthenes came up with this method. So you can see there's like a pylon marked A, which is Alexandria, near the mouth of the Nile River on the Mediterranean coast. And S marks the location of Cyrene, on the town on the, or city on the Nile River. And he was aware that on a certain day the sun would be directly overhead in Cyrene, and you could basically look down a well. When the bottom of the well was perfectly illuminated, you know the sun was directly overhead. And he arranged to measure the angle that the shadow of the sun made in Alexandria on the same day, at the same noon, basically noon on the same day. And so he used the simple geometric method, measuring the distance between Cyrene and Alexandria. Knowing that angle alpha, he could calculate the radius of the Earth, and it's believed he got it to within 10%, which is pretty good going for those days. Now on to Hipparchus of Nicaea. He was famous for, well, first of all, he adopted the Babylonian Sumerian system of measuring angles, produced the first known comprehensive catalogue of stars. The original catalogue is lost, but it's believed to be the basis of the catalogue in Claudius Ptolemy's Almagest. He also came up with a system of ranking stars, and the legacy of that is still around today, where he ranked stars in the order of the brightest, rank 1, to the faintest, rank 6. And that system has been extended to things that are much brighter, such as the sun, magnitude minus 26 point something, down to the really faint stars that can be detected on long exposures of the Hubble Space Telescope, maybe magnitude 32. He also discovered the precession of the equinoxes by using ancient observations of star positions. He realised that the crossing point of the celestial equator and the equinox was actually changing over time. As far as we know, he was the first to realise this. And he also calculated the length of the year as 365 days, 5 hours, 55 minutes, 12 seconds, plus or minus 15 minutes. And his value was only 6 minutes out from the current accepted length of the year. So you can see the story here, that the precision is improving as we go forward in time. Better methods, they've started to use better instruments. I didn't talk much about instruments used by the Greeks, but they basically had, because they were quite good at metallurgy, they could make fairly accurate circles with scales on them for basically measuring the altitude of stars, things like that, and positions of stars. And he came up with a geometric model of the solar system. It was a geocentric one, so he still followed the geocentric idea that the planets and the sun, moon all orbited the Earth. But he came up with a scheme involving eccentric difference and epicycles to explain the motion of the planets. We'll now moved on to Claudius Ptolemy, who picked up where Hipparchus left off. He basically also, apart from improving the star catalogue of Hipparchus, he gave a list of 48 northern centric constellations. Obviously, you're not going to find the Southern Cross or things like that in there because he couldn't see those from his latitude. So he divided the sky he could see into 48 constellations. Some of them closely relate, or a lot of them closely relate to the modern accepted constellations. He also made an improvement of Hipparchus' model of the solar system. He invented some more artifacts to get better results, particularly a thing called the equant. And I'll just refer to this diagram here to explain how these models work. If you're not familiar with it, the outer planets like Mars, Jupiter, and Saturn, when you observe them on either side of conjunction, they don't move through a steady path relative to the fixed stars. They actually start to move backwards and then go through like an S curve against the background stars. So sometimes they're moving what's called retrograde motion. And this was a bit tricky to explain. If they were just moving around the Earth in circles, it didn't really make any sense. So the first trick was to, instead of the Earth being the exact centre, and this is already kind of a cheat because you're going away from a geocentric model, you have the deferent centred not on the Earth, but on some arbitrary point that's actually not on the Earth. And then you have a thing called an epicycle, which is another circle where the planet is rotating around a point on the deferent circle. And to get the speed of the motion of the bodies to come out correct, he invented another funny point called the equant, which he used so that the revolution about the equant was at a steady rate. To explain the non-steady rate of the motion of the planets. So clearly this is really an artificial looking system. Yeah, I mean, you could keep adding all sorts of funny things onto this. And in fact, there's not a lot happened for a long time in major advances in astronomy. There was a lot of invasions going on around the place. Some of the Rome got invaded. Greece was attacked. There were a lot of tumultuous times and going on for a long period of time. But in the Middle East, areas of under Islamic rule came to a more settled way of life, and some really interesting scholars came about. But this guy, Ibn al-Haytham, otherwise known as al-Hazem, made some interesting advances to optics and actually the general concept of science. So one of the things he read was well familiar with Ptolemy, but he really didn't like all of these artificial things in the theory, particularly objected to the equant, because it failed to satisfy what was believed to be the theory of uniform circular motion. And he thought it was absurd having physical motions controlled by arbitrary imaginary mathematical points, lines and circles. So he was criticizing it from a philosophical point of view. He thought that there must be a better solution, but he did do a little bit of work on this, but he was mainly interested in other things. He did some great work on optics, including because obviously glass lenses had been discovered by this point. Not the telescope though, but things for eyeglass correction to the human eye. Did work on the anatomy of the eye, but he did some experiments that showing that light through air travels in straight lines, whereas people had just assumed that, but he did experiments to show that that was correct, and he was a proponent of the concept that a hypothesis must be supported by experiments based on confirmable procedures or mathematical evidence. So he was an early pioneer of what was becoming the scientific method 5 centuries before the Renaissance scientists who are generally credited. But just a little bit about instrumentation. The Greeks had some stuff for measuring positions, but not much had changed until the Middle Ages. And one really important improvement was a portable way of accurately measuring positions of stars. It was actually better than the methods that Greeks were using, and it was portable, so it could be used by navigators, sometimes called Jacob's staff. And the way it works is you have a cross piece on a pole, and you can either alter the length of the pole as shown in the picture of a real one at the top, or you can slide the cross piece up and down the pole, and it has a measurement scale, and you basically line it up by moving the cross piece up and down, or lengthening and shortening the staff. And you could use this sighting from where you see the picture of the eye there, sighting from the base of the staff through the points at the end of the cross piece, and this could give you quite accurate angular measurements. And of course, because you can hand hold it, you can use it on a ship, so it was quite important for navigation. And a similar instrument was also known in China, so it's not actually known where this was invented, whether it was independently invented in several places, or maybe it was learned about and it just the information became known. Okay, we come to Nicholas Copernicus, and the diagram there shows a diagram of his model of the solar system, showing the sun at the center with the planet orbiting it, the moon orbiting the Earth. And this concept, it's thought that he wasn't actually aware of Aristarchus. So he just liked this idea because he also disliked the complexity of Ptolemy's system, and he thought this was a lot more elegant. So he spent a lot of his life researching this, looking up measurements and doing his own observations, and tried to come up with a system where the the heliocentric model he developed was just as predictive as Ptolemy's model. And it was basically his life's work, called De Revolutionibus Orbium Celestium. And he was very reluctant to publish it because he thought it would be ridiculed, or worse, he would get accused of possibly heresy. But eventually his student Rheticus, who was really keen on the theory, convinced Copernicus to publish it. So he arranged for the document to be printed. Now, the printer, Andreas Osiander, who was a reasonably knowledgeable person himself, realised this was going to cause a big controversy. So he added his own unauthorised forward as an explanation. He said, different hypotheses are sometimes offered for one and the same motion, and therefore the astronomer will take as his first choice that hypothesis which is the easiest to grasp. These hypotheses need not be true or even provable. If they provide a calculus consistent with the observations, that alone is enough. So this was basically stopping the criticism in its tracks that this would go against the ideas of Aristotle, which were well accepted by theologians. And they'd actually built a lot of theological things on the ideas of Aristotle. For example, that the earth should be unmoving. So this could be a challenge to the authority of the church. So Osiander thought he had to be really careful about this. But it's thought that Copernicus by this time was an old man, and it said that he was presented with the first copy of the printed work and then passed away. It was basically on the day of his death, according to legend. And of course, it did cause a big controversy. Anyway, I won't go into that too much, but we'll move on. Tycho Brahe. Now, he was a wealthy noble, Danish noble, and he was extremely wealthy. But he was, as a student, he was interested in astronomy, and he noted that he was observing a conjunction. I think it might have been just Jupiter and Saturn. He noticed that both the Prutenic tables, which a mathematician had used Copernicus' method to compile, and the Alphonsine tables using Ptolemy's system, both of them were pretty poor failure at giving a good prediction of exactly when the conjunction was going to occur. And he thought, well, it may not be because of the theory, it could be because the tables are bad, because they're relying on measurements that are not so good. So he decided to establish a new observatory, and it would be equipped with the finest instruments of the day to try and resolve the matter. And the result shown in the picture is the observatory of Uraniborg on the island of Hven. And he basically hired a bunch of astronomers to carry out the observations, paid out vast sums of money for the finest craftsmen to build the best quadrants and other star position measuring instruments of the day. And remember, this was all before the telescope, so these instruments still relied on the unaided eye, just sighting along notches and things like that. So the limitation is actually the resolution of the human eye. He also, after a while, came up with his own idea, which looks really strange. He thought that, well, would settle the difference, and instead of having either Copernicus or Ptolemy, would split the difference and would have the planets orbiting the sun, but the sun and moon in turn orbiting the Earth. And this is known as Tyconic Theory, and it was reasonably popular for a while. To us, it looks particularly bizarre because it's neither Earth-centric nor sun-centric. So we now come to Galileo and the telescope. Galileo favoured the theory of Copernicus, and he heard about the invention of the telescope by the Dutch spectacle makers. And as soon as he could, he made his own and turned it to the sky. And he noticed a couple of really important observations. The first one is the phases of Venus you see at the top. If Copernicus was correct, then you could never see the planet Venus would never show phases. So this kind of is a disproof of the Copernicus theory. It doesn't actually, strangely enough, it doesn't disprove Tycho's theory, but nevertheless, this was a really important observation. And in his notes below, you can see his observations of the planet Jupiter and these tiny stars that are in different positions around it over time. And he realized these were actually moons orbiting the planet Jupiter. And so he thought, well, he knew it was pretty sure the moon orbited the Earth. And now we see an example of another planet having things orbiting it. And he immediately realized the importance of this, that planets could have things orbiting them, but everyone agreed that Jupiter orbited either the sun or the Earth. So it was a pretty strong indication that Copernicus and Aristarchus were actually correct. There were still a lot of objections, and Galileo, as you're probably aware, got into trouble and ended up in house arrest, and was told became subject to the Inquisition. Okay, and Johannes Kepler. Now he was around at the same time as Tycho Brahe and Galileo, and he was a skilled mathematician, but he found himself at odds with the Lutheran Church on some matter of theology. And unfortunately, because this was known, he was unable to get employment at any Lutheran university. So he kind of in desperation applied to Tycho Brahe because he heard Brahe was seeking to employ astronomers. So he applied for a position, and he was hired, although Kepler was not always in the good books of Tycho Brahe, because Kepler had written a letter praising a guy called Ursus, who was a big rival of Tycho Brahe. So that didn't go down too well. But Brahe realised Kepler's mathematical skills, so he took him on. Also, Kepler didn't have very good eyesight, so he wasn't much use for doing the kind of accurate observations that were required. So he was set to work doing calculations, but he was only allowed access to dribs and drabs of the data that the astronomers there had collected. Tycho was very jealous of access to this data because after an incident with Ursus where he believed his work had been plagiarized. But it turned out that, sorry about that, Brahe had a big falling out with the new Danish king, and eventually he was forced to abandon Uraniborg. Basically, his source of funds were cut off, and he had to actually, like Kepler, actually look for a job. But he was given a position at the imperial court of Rudolf II, the Holy Roman Empire, of the Holy Roman Empire, as court astronomer. And Kepler and a retinue went along with him to Prague. Sometime he'd been in Prague for a while, but he eventually died of a bladder infection. There was some suspicion that he had been poisoned, possibly even by Kepler, but this has been proven false because eventually, not too many years ago, actually, they had his body exhumed and there was no sign of any residue of any poisons. So they're pretty sure that the story he just died from an infection is probably true. But this led to a problem. Kepler couldn't finish his work. He didn't have access to the data, but eventually he came to an agreement with Tycho's ears, and he was allowed access to all of the data from Uraniborg, provided that the Tycho Brahe was given due credit for any work that Kepler published. Yeah, it's interesting that the data from Uraniborg had an accuracy of about 1 minute of arc, and it's not a coincidence. That's about the best you can do with the human eye, and until the invention of the telescope. And it just so happened that this was a good accuracy for Kepler to make sense of the data. If it had been a lot more accurate, it would have been really difficult to make sense of it. But it's accurate enough to come up with the useful conclusions that Kepler came to. We'll move on a bit more quickly. Kepler's first law of planetary motion, he found that the best fit in a heliocentric model was that the planets were not actually traveling in circles, but they're ellipses. And this one here is highly exaggerated. The sun is at one focus of the ellipse, and the planet orbits. In reality, the Earth, for example, is only a little bit eccentric, so this would be none of the planets' orbits in our solar system are this eccentric, although there are some other solar systems we know of now where there are planets with this kind of eccentricity. Another law, basically what this is showing, that the planet sweeps out equal areas in equal times. And basically what this means, when the planet is closer to the sun, it goes faster, and when it's further away, it goes slower, in just such a way that the area A and B turns out to be the same area. So he was able to work that out from the data. And the other one is Kepler's third law, also known as the harmonic law. So he deduced that the period of the orbits, in other words, the time the planets took to orbit the sun, if you squared that, then that was proportional to the cube of the semi-major axis of the orbit. In other words, the long axis of the eclipse, halved, is the semi-major axis. So the cube of that was proportional to the square of the period. This is sometimes called the harmonic law. So Kepler used these laws to publish a set of tables that are called the Rudolphine tables, in competition against the Prutenic and the Alphonsine tables, and these were hugely more accurate. So it was now possible, for example, to predict transits of Venus. Basically, that was a major success for Kepler's laws. I'm aware that I've talked a bit long, so I might go quickly through these things now. We're getting up to Sir Isaac Newton. Came up with universal laws of mechanics that he believed not only applied on the Earth, but everywhere in the universe. 3 laws plus a law of universal gravitation, which basically said that every particle attracts every other particle in the universe that is proportional to the product of their masses and inversely proportional to the square of the distance between their centers. And these laws, along with justifications, were published in Philosophiae Naturalis Principia Mathematica, sometimes just shortened to Principia. This was supposed to be funded by or financed by the Royal Society, but they were basically broke. So Sir Edmund Halley had to pay for it out of his own pocket. We're glad that he did, because otherwise we might never have had this. And it turns out that using Newton's laws, you can derive Kepler's laws from first principles in the case of the two-body problem. But we know that if you apply the laws in full, every planet acts on every other planet. So the small variations in the orbits that we can see today with modern measurements, if Kepler had seen those in his data, he would have been probably horribly confused about what was going on. Quite interesting. The one thing that Newton's laws fell over on was the issue of the planet Mercury. The orbits of the planets, the ellipses aren't fixed in space, they slowly precess around the sun. And in the case of Mercury, the precession is fastest. And Newton's laws do actually predict precession, but not quite enough. So that was an outstanding problem until the 20th century. Okay, quickly mention another important thing. James Bradley, now that we had the telescope, he wanted to look for stellar parallax, but he initially thought he had been successful, but after looking at the actual pattern of what he was observing, that the stars' positions were moving, but they were changing in a position in such a way that he realized that it was nothing to do with parallax, but it was actually caused by the motion of the Earth around the sun and the fact that the speed of light is finite. So it takes time for the light to travel. So because the Earth is moving, it actually creates an angle between the line of sight of the star and your telescope. So this effect is known as the aberration of light. So it's a demonstration that, in fact, the speed of light is not infinite, as was possibly assumed. Finally, Friedrich Bessel really did discover parallax using an instrument called a heliometer. And there's a picture or an illustration of the one he used. It was built by Joseph Fraunhofer. And it's called a heliometer because what they were actually used for was measuring the diameter of the sun. You think, well, why would you want to do that? Well, you're trying to work out the motion of the Earth around the sun, and one way to do that is to monitor the apparent size of the sun. As the Earth orbits the sun, it's a different distance. When it's further away, the sun appears smaller. So they wanted to get a really accurate measurement of the size of the solar disk during the year. And so this instrument called a heliometer was invented to do that. But it was realized that the same instrument could be used to really accurately measure the separation of stars. And one thing this did was it was incredibly more accurate than any other method up to that time of measuring the separation or the distance between objects. The way they did it with the sun is you would start with two images. Well, I'll actually show it in the next slide. It makes a bit more sense. This is what the front end of a heliometer looks like. You can see the objective lens is actually cut in half. And you can move the positions of the two lenses using that handle. It had a micrometer gauge, so you could work out how much you'd moved it. What you would do is line up the image of the two half images of the sun, or the images of the sun edge on edge, and then wind the screw until the two images align and work out how far you'd had to do the move, and you would have an extremely accurate measure of the angular size of the sun. Same trick with stars. So if you don't know parallax, this is a quick diagram showing a distant star measured from the position from the Earth 6 months apart compared to a background star, and it looks like the position of the foreground star appears to have shifted against the background star, and measuring the amount of shift you can work out the parallax angle. And if you know the diameter of the Earth or the radius of the Earth's orbit, you can calculate the distance to the star. So in fact, the first star was done with 61 Cygni, and that star was chosen because it had a high proper motion. It was moving against the background of stars quite rapidly, which indicated to those astronomers that it must be relatively close compared to the other stars. So that one was a prime case, and Bessel managed to get a parallax of something like 0.3 of an arc second. which is an incredibly small angle, really, when you think about it. Not by today's standards, but it was then. So we had parallax, and so parallax is a really strong indication that the heliocentric model was correct. The aberration of light shows the Earth is actually moving. So basically all of the objections to heliocentric theory have now been answered. So there's just the question now of the problem of the precession of Mercury's orbit. So how do all sorts of ad hoc ideas will come up with that? There was something weird about this, the distribution of matter in the sun that might be causing it. But Albert Einstein came up with the theory of relativity, and the special theory basically says the laws of physics are invariant of all frames of reference at rest or under uniform motion. This wasn't controversial at the time. Basically, Newton's theory is more or less the same, or it wasn't kind of expressed in these terms. But what does depart? The speed of light in vacuum is invariant in all such reference frames. And for this to be possible, the only way it can happen is that time can no longer be independent of the observer's state of motion. Newton had just made the assumption that time was the same everywhere. But Einstein said, no, if you're moving, you will measure time differently to an observer at rest. And one of the implications of that in his paper on the electrodynamics of moving bodies shows that this means that energy and mass are equivalent, and you come up with the famous equation E equals mc squared. So this is all very well, but Einstein wanted to explain gravity, and gravity didn't really fit into his relativity particularly. And in fact, he discovered that putting gravity into the theory was really difficult, and eventually came up with it. And he came up with this equation, not in exactly this form. This is a modern tensor notation for the theory. So you've got the tensor G is equal to 8 pi times the tensor T. And basically, if you write it out in full, you get a system of 10 independent nonlinear differential equations. Sounds pretty complicated, and it probably is. The tensor G representing the curvature of space-time, and the tensor T is called the stress energy of the system, which includes stuff like matter, radiation, and actually even pressure. So to get a bit of a handle for the layman what this means, there's a book called Gravitation written by Meissner, Wheeler and Thorne, which gives a qualitative explanation of this equation. It says space tells matter how to move. In other words, matter moves along whatever the shortest path is, and matter tells space how to curve. And because space is curved, the shortest path isn't necessarily a straight line. So he basically has taken gravity away from being a force to just gravity is basically curvature of space-time. The sun is causing space-time to curve. So the Earth, as far as the Earth is concerned, it's just following, if you like, the path of least resistance, just a straight line, but it's curved through space. If you looked at it on a sort of an infinitesimal area, it would be a tiny segment of a straight line, one way to think about it. So in doing this, Einstein has abandoned Euclidean geometry, which had been held since ancient times. Not familiar with the work of Euclid, he wrote a book called The Elements, which gives the theory of geometry where, based on a set of axioms, he derives all of geometry. And one of the axioms, called the parallel postulate, is what is being abandoned here. To make sense of it mathematically, it turned out mathematicians had already been working on the mathematical theory behind this. So Einstein already had some mathematics he could use to explain how this would actually work. So important predictions. I talked about the precession of perihelion of Mercury. Newtonian physics unable to fully account for this. It was short by 43 seconds of arc per century. It doesn't sound like much, but remember, even in those days, they were getting pretty accurate measurements. And there was this unexplained additional precession. For a long time, they thought, oh, there was some invisible planet orbiting close to the sun or something like that. But Einstein used his theory to calculate the orbit of Mercury, and the conclusion was that 43 seconds of arc discrepancy disappears when using his theory. He also expected that the light, any light from background stars passing near the sun would be deflected, and the amount, and predicted exactly what the amount of deflection should be. So Eddington carried out an expedition to go and measure this on a solar eclipse, where of course the moon is blacking out the sun, so for a short period of time you can see the stars close to the sun in the sky. So he undertook to photograph this. He was successful, and he was able to measure that. In fact, yes, the deflection of the positions of the stars varied depending on how close they were to the sun, and exactly the way Einstein had predicted. So since then, this has been measurements being redone much more accurately with the Hipparcos astrometry satellite, and probably with Gaia as well. And Hipparcos can actually detect this effect as far as 60 degrees angular separation from the sun. So even at that separation, there's still a very tiny deflection of starlight caused by the sun's gravity. Another important thing, black holes. So Schwarzschild was actually able to find a particular solution to Einstein's equations. In the case of the orbit of Mercury, Einstein simplified things and basically came up with a linearized approximation. Solving the actual orbit of Mercury in general relativity would be very difficult, could only be done numerically. But Schwarzschild came up with a solution for basically a point or a spherical body, no rotation, so static. And he noticed that any body had a peculiar property associated with it called the Schwarzschild radius, given by that equation at the bottom, 2 times the gravitational constant multiplied by the mass of the object divided by the square of the speed of light. And this defines a surface called the event horizon. And it turns out that at that position, the escape velocity is equal to the speed of light. So in other words, anything light cannot escape from within inside the event horizon, because you need a speed faster than light to get out. So this actually applies to any object, like even an atom, but it turns out the Schwarzschild radius of an atom is so far inside the atom that you don't actually get a black hole. Similarly with a planet or a star. If you could compress those objects down inside their Schwarzschild radius, they would actually be a black hole. So we know that this has been astronomically confirmed observations of the black hole at the centre of the Milky Way by observing the orbits of stars. There's some object there in a very tiny region that has 4 million times the mass of the sun. The only reasonable explanation would be a black hole. Similarly, the event horizon cameras have been able to image the region just outside the event horizon in the case of the giant elliptical galaxy in Virgo. So yeah, it's pretty well understood now. And this is the final slide. I've gone a bit over time. We come now to modern cosmology. Now, of course, Albert Einstein, because he believed his general relativity was universal, he thought, well, it should be able to explain the universe, so why wouldn't he do that? But he, to his not exactly his dismay, but his surprise, he thought astronomers were telling him that the universe was static. There were stars everywhere or at great distances, but nothing much was happening. So he plugged this into his model and he discovered that general relativity said that a universe that's static is unstable. It would just basically collapse in on itself. So he thought, okay, what do I do about that? He added a fudge factor to his equations called the cosmological constant, which basically was like, you can think of it as anti-gravity. And this constant exactly balanced the gravity of all the matter and radiation in the universe. It's a bit of an ad hoc kind of thing, but it does give a static solution. A little while later, Edwin Hubble discovered that, in fact, the universe wasn't static, it was actually expanding. So Einstein thought, oh, well, okay, we don't need the cosmological constant because the universe expands if it had a initial impetus and doesn't have enough matter to stop the expansion. So Lemaitre came up with this idea of the Big Bang, that there was some primordial state of the universe and it just blew out into the universe and expanded into the universe we see today. So this has sort of been worked on, and the modern version of it is that we realise that Einstein's gravity can't explain exactly what happened in the Big Bang. So we call on another theory of modern physics called quantum theory, and that there was some kind of quantum field called the inflation field that somehow kicked off the Big Bang, and the universe underwent a massive expansion inside that made it more or less Euclidean on large scales. That's known as inflation. And then over time, standard general relativity takes over, the universe cools, atoms form for the first time, which allows light to flow through the universe. The aftermath of that light is called the cosmic microwave background, shown on the diagram here as the afterglow pattern. At that point, the universe was already 375,000 years old. And we go into the dark ages because stars hadn't formed yet. There was just this background light that was gradually expanding, cooling as the universe expanded. But then matter starts to congeal, first stars form, and light is again in the universe. And the universe has gradually expanded since then. But current observations say that there's something strange going on, because it's not just expanding as you would expect from general relativity. Some kind of extra expansion is happening, or accelerated expansion, and so the concept of dark energy is introduced, and so effectively Einstein's cosmological constant is back, because, well, that's one thing that could explain dark energy. Anyway, I'd better leave it there. So we've gone from the Stone Age to pretty much current cosmology. No idea where it'll all end up, but yeah, any questions?
No questions. No questions on the chat today.
Okie dokie. I'll remember Jenny will be along next week to talk to about the work at her home observatory. So it should be really interesting. Okay, thanks all.